আচ্ছা, একটু বুঝাই নেই তাহলে কপি করতে ইজিয়ার হবে। সো একটু স্ক্রিনে দেখো কি হচ্ছে এখানে। Just a quick recap of what we did so far. So we learned that there's this equation for simple harmonic motion or oscillation based on an object going in a circle like that. We found that the equation for displacement is given by this function here, x equals x naught cos omega t. So we wanted to figure out how to find out other quantities from here. So the base function was displacement. So this is the graph for displacement versus time. And the graph for displacement versus time is going to be this function, which is x equals to um, x naught cos omega t. Now this can be cosine, this can be sine. It depends on what part of the oscillation you're starting from, but we are using this as our base function. Okay, so আমাদের equation হচ্ছে এটা, which is x equals to x naught cos omega t. Can anyone remind me what was x here? What would the description of x be? This displacement would be fine because we are not really sure কি হচ্ছে এখানে, so just displacement is fine. Displacement, what is x naught? Maximum displacement, correct. Maximum displacement. And last class, some of you had trouble with the omega here. What is the omega? Angular speed, right? Angular speed. However, which formula is used to find omega? 2 pi divided by t, right? And time period tells আমাদের জানা আছে. So yeah, that's the equation that we have for your oscillation. This is the displacement time graph. And then if you take this equation and plot a graph এরকম দেখতে আসে. So it's a what function? Cosine function. You have seen that before, right? Maximum being x naught and minimum being minus x naught. So that's the graph. It's a Fisher graph actually. So if you want to see what this graph is about, it's essentially this thing that I showed you the other day, simple harmonic motion or oscillation. What the heck? So we haven't proven yet that it's a simple harmonic motion, but anyways, it so yeah, there you go. This is your object moving in a circle, and we found that as this object goes up and down, right? আমি যদি এই যে orange ballটার হচ্ছে graph plot করি, the one that's going in a circle, right? Graph plot করা খুব difficult. কেন? Because the orange ball is doing two types of displacement here. What displacements are the orange ball doing? Horizontal and vertical, because it's going up and down, left and right. So it's moving horizontally and vertically simultaneously, right? Kintu, আমি যদি side থেকে দেখি এটাকে, let's say rotate this disc and I see from the side, right? I can see that this is only going what oscillation here? Vertical. Up and down is just vertical, right? And then if I look on the right hand side, there's a mass spring system. যেটা circular motion করতেছে না. But if I turn down the lights, right? Would you be able to differentiate which one is what? No, right? So doesn't it mean that they are exactly identical in every manner? Their time period, their displacement, their oscillation, angular speed, সবকিছু same, right? These kind of motion are referred as simple harmonic motion because they have a hidden what component in them? A circular motion. So springta is not going in a circle, but the vertical oscillation of the spring replicates what? A circular motion, right? So we found that the graph that we get here is this function here, vertical oscillation je hocche. If you want to know at which location the mass is at any given time, this is the function. And I did a math with the pendulum the other day, if you remember. This was the question. We found where the pendulum can be at any given time, right? Using the expression here. Anyways, so that's the equation that we saw last class, but then we did something else. We wanted to find what from here? The equation and graph for what function? Velocity. Now, if you remember from your O levels, there was a way to get velocity from a displacement function. What was it? Differentiation, right? So if I differentiated this function here, I should get velocity. And that's exactly what we did here, right? So this is your velocity time graph here. So the velocity time graph comes from where? It comes from displacement function থেকে differentiate করলে velocity time graph. So what do you get when you differentiate your velocity function? So dx by dt data, and then we found that we get this expression here, which is v equals to minus omega naught sine omega t. And I told you that if you want maximum velocity, what should this part of the function be? 1, right? Because what's the maximum possible value for a sine function? 1. So maximum velocity equation is omega x naught. So if you ever have an oscillating system and you want to find the maximum velocity of that oscillating system, right? What do you use your equation as? Just this omega x naught, okay? And then we found the graph. The graph is a negative sine graph. You'll find some interest in outputs here. So when your displacement is maximum, your velocity is what? 0, right? It makes sense. Look at this. If this is a pendulum, right, going back and forth like that, when the displacement is maximum, it comes to this point, right? What is its velocity? 0. And when the displacement is 0, velocity is what? Maximum, because all the GP gets converted to what? KE, right? So if you look at this, isn't the displacement 0 here? But do you see that the velocity is a maximum there? Our GP is highest. So once it comes to the center, all the GP is lost and it's converted to what? K. That's just the fastest at that point, right? So yeah, this is the function for velocity. There's another equation for velocity. I'll show you later on. And then last thing we wanted to find what from this graph? Acceleration versus time, right? So how do you get acceleration versus time from a velocity function? Once again, what do? You differentiate it. So I'm going to differentiate for a part of important. So I'm going to show you right now. So look at this. This is the function for velocity. dv by dt gives you what? Acceleration, right? Now acceleration function theta minus omega square x naught cos omega t. And I'm going to explain a part x naught cos omega t is actually what? Yeah, it's just x, right? So what we can do now is we can replace that here, and we come across this one formula. Last but our this equation that you see here, a equals to omega square x, right? It's actually something we have done before. What was it? Centripetal acceleration. Centripetal acceleration in circular motion is what? A equals to omega square r. This is the same thing. Now, we could have said, and students have this argument, match pari. Like, look at them. They're going circular motion. Match they can mimic each other, right? And they might not be a circular motion. But what more evidence do you need than the fact that the acceleration for this is also the same as what motion? Circular motion. So eventually, the point I'm trying to make here is that a spring going up and down is actually a circular motion in which axis? Vertical axis. A pendulum going left and right is actually a circular motion in which axis? Horizontal axis. And these kind of oscillations are referred as what? Simple harmonic motion, right? So how would you know if your oscillation, random active oscillation, is simple harmonic, right? So I'm talking last class, maybe I showed you partly the cantilever. Is the cantilever. Okay, that's actually oscillated there, and I can change the frequency there. You see that, right? So the question in a past paper was, is this simple harmonic motion or not? How would you find this? It's a paper 5 planning question, right? So what are you supposed to do? So you're supposed to find the what of this thing? Acceleration. And what are you supposed to find? Displacement. And then see if it gives you this relationship or not. So eventually, if anything does actually obey simple harmonic motion, what would the graph look like for acceleration versus displacement? Here come the graph. So if my x-axis or y-axis, let's say acceleration meter per second square, and this is displacement in meter, what do you think should the graph look like? Yeah. Right. Which way? Right. Correct. So it's going to be this graph. And in any oscillation that you have, right? Any oscillation out there, if it's a straight line passing to the origin with a negative gradient for acceleration versus displacement, you can say for sure it's a what motion? Simple harmonic motion. Okay. So this is the final step. So yeah, there you go. These are the graphs out there. Can you tell me what should be my axis here for maximum? Maximum to key over here, a function to the. So what should the maximum value here be? Yeah, omega square x naught. Okay, so this is going to be omega square x naught, and that's going to be minus omega square x naught. Right, so that is it. This equation tells you that this oscillation obeys something known as the simple harmonic motion. simple harmonic motion is a random oscillation that follows circular motion within it. Right, so copy part by part. First do the displacement velocity part, then the other one. Are you expected to do this in the exam? Yes, they'll give you graphs of random nature. You need to differentiate them. You need to figure out what the gradient is, right? So graph analysis is a lot in this topic. What is a negative sign supposed to be there? Oh, very good. Negative signs are meaningless. Like I'll come to that in a minute. So the negative sign has a very important role here. The circular motion equation is -9. So negative key mean করে ওটা আমি দেখাচ্ছি। Oh, acceleration that. Page 75. Done it. Just a second. Okay, let's see something else. Look at this. I think you probably have seen something like this before, but now it'll make a little bit more sense. So do you see that the spheres are undergoing circular motion here? And look at the whole sphere system, right? Isn't it just like a circle, right? But যেটা এখন করবো একটু focus করো, যে কোনো একটা sphere কে select করো and just see what it does. For no, just follow one sphere and see what it does. Any one sphere, you'll find that it's only moving in a straight line, right? So they're just going like up. Just you can like a sphere ke follow karo. So don't look at the big picture. Just see one sphere. You'll notice it's just going up and down, and it's not doing anything else, right? So similarly, all the spheres are just going up and down. But the way the thing is timed, right? When you see from far, right, it does look like what's actually going on here. There's actually a circular motion going on, right? So this kind of a system is called simple harmonic, which means that the objects individually are doing their own motion, but they're actually a part of a bigger what motion? Circular motion, right? I'll show you one more. These are plenty out there. Naturally, hoina because energy loss and whatnot. But yeah. Like in real life or? Oh, that's an animation. Wait, you didn't figure that out? Of course, it's possible now. It's this is another one. So what actually is vertical motion, right? Just look at this. দেখলে মনে হবে যে they're going in circle, right? But actually কিন্তু circle এ যাচ্ছে না। যে কোনো একটা ball কে তুমি যদি focus করো, it's just going which way? Up and down. Just যে কোনো একটা ball up and down যাচ্ছে। But এই যে এখানে look at that chaos, right? এখানে কিন্তু সবগুলো just going up and down. But দেখতে মনে হচ্ছে না it forms a circle. That's because the object that's moving here or time period or velocity changes or displacement changes, সবগুলো is actually a part of what motion? A circular motion, right? So once you combine all of them, you're basically drawing the individual points on a circle. And সবগুলো combine করলে, so if I have infinite number of spheres here, right, what would you actually see? A circle, just a big circle out there, right? So you're basically plotting individual points of the entire circle here. So yeah, these kind of motion is referred as simple harmonic. And there are only two that can be done in your syllabus, pendulum and a mass spring system. Okay? Right, so before I move on, so look at this. There are three equations of velocity out there, and this chapter, students have a bit of struggle with figuring out which equation of velocity is appropriate for the question. I'll teach you right now konta use korte hoy, okay? So, please screen it. So if you're given a random time, মানে ধরো একটা time provide করলে and they're asking you what the velocity at that time instance is, right? This is the equation, and kind of obvious what's there in this equation, time, right? But sometimes they'll ask you a question that what is the velocity of an object at a particular location, time dynamic. যে object oscillate করতেছে, oscillation এর amplitude হচ্ছে 12 centimeter, 5 centimeter, what is the speed? আর কোনো time period কিছু দেওয়া নাই. There's a formula, this one, which is v equals to omega root over x naught square minus x square. X naught being your maximum amplitude, x being the amplitude at which you're trying to find your speed. এটা দিয়ে হচ্ছে you can find when displacement is provided. এটা একটা catch আছে. When you find the answer, it'll give you a what velocity? Plus and minus, right? Cannot. Yeah, because remember last lesson we saw that if something is crossing a point in an oscillation, it will cross that point two ways. Once going sideways, once coming back. So at that particular location, you will have what velocity? A positive velocity, and then on the way back, a negative velocity. So it is just inevitable, okay? So that's why you have this root over here, which will give you like a plus minus that tells you that velocity can be plus minus, right? And this one is maximum velocity equation, which is kind of self-explained. If you want maximum velocity, you just need to know the displacement and the time period. The answer to that, okay? So yeah, I did to copy it here. Yo-yo. No, yo-yo is a little different. It's an oscillation, but there's a different branch of physics involved in the yo-yo. It's called moment of inertia. It's just like, you spin something and the thing unwinds again and then spins back again. So it's moment of inertia. So it's a little different from simple harmonic motion. done the equations? Acha, এখন what we'll be doing is we'll try to write down the definition of simple harmonic motion. It's probably one of the most common questions in your paper. Anytime a chapter থেকে question আসে, you will get a simple harmonic motion key for 3 marks. Okay, so এটা হচ্ছে আমরা এই পেজে পাবো, page 76 এ যাও. So what is the definition of simple harmonic motion for 3 marks? 3 marks equation টা দিতে হয়, but let's write that down. So definition is essentially writing the equation. And what is the equation here? A equals to omega square x, right? So how do you put it in words? So, I mean, yes, that's good. Okay, so that's one step of it. Acceleration is directly proportional to displacement, but there's a couple of more marks, right? Cannot. So did they? Yes, right. So the equation there's a minus sign out there, and the minus sign plays a very important role. We'll see that right now. Okay. So the actual definition of simple harmonic motion, it is a motion in which the displacement is keyword here directly proportional directly proportional to the acceleration, and more importantly, the displacement or the acceleration always acts in the opposite direction. Displacement. Or there's an alternate version out there. What are the it's a motion in which displacement is directly proportional to the acceleration, and the acceleration always acts towards the equilibrium center. Okay. So if you have a motion and you are wondering if it's simple harmonic or not, right? It needs to fulfill this criteria that the acceleration must be directly proportional to what? Displacement, and the acceleration must always act in the opposite direction of displacement. So if your acceleration is positive, you'll find your displacement is negative. Or if your displacement is negative, your acceleration is going to be what? Positive. What does that mean? They act in opposite direction, right? And we have very good evidence of that. So to screen it, look at the two graphs that we had here. This was the graph for what? This one, displacement. This is the graph for what? Acceleration. Do you see they're exactly the same graph, right? But there's this one single difference there. What is it? Opposite, right? So when your displacement is positive, your acceleration is what? Negative. When your displacement is negative, your acceleration is what? Positive. But I understand it's a graph and the math and everything, but what does it actually mean? So there's actually a practical implication here. So if you take this object here, right, and let's say তোমাদের right case and left, so left এদিকে, right এদিকে. So left এ যদি আমি এটা displace করি and I release this, right, it's now displaced to the left. Which way is the force acting? To the right. And as it crosses the right, like, crosses the center and goes to the right, which was my force? To the left. So you'll find that যেদিকে displace করে, your acceleration is always which way? The other way. And it acts towards the what of this motion? Towards the center, which is the equilibrium, right? Doesn't that seem very similar to circular motion? A circular motion, what was the requirement? There must be a force, a resultant force, always acting towards the what of the circle center, right? So simple harmonic motion requirement of chip A is directly proportional to X, obviously, they must be in opposite direction. And that's the reason why a yo-yo is not the answer. Okay, because yo-yo the forces, there's no center there. It just spins around it and then goes back to your hand, right? There's no oscillating center. So you can't consider it to be a simple harmonic motion. So yeah, I will give you some random examples right now. তোমাদেরকে figure out করতে হবে, are they simple harmonic or not? Okay, so এখানে force যেটা act করতেছে to the center, do you know which force is that? Restoring force, but like what is the force? Centrifugal. I'm saying in terms of this. Yes, what was it? Component of weight. Yes, exactly. Remember the conical pendulum? Conical pendulum is a component, so that's the component of tension here. That's a horizontal components. So that's what's taking it inwards. Our vertical component data, just such a weighted interact with. করতেছে। So once it goes towards the center, the force that actually takes it towards the center is T cos theta. যদি theta ওটা হয়, মানে এদিকে হয়, মানে basically the horizontal component. Okay. Right. So I'll give you some examples. You need to figure out for me, are they simple harmonic or not? Okay. So. Yeah. Yeah. So I'll show you another version. Yeah, this is a much more classical example of simple harmonic motion. That would give it are easy. I'm going to say pendulum night, but this is actually exactly simple harmonic. Okay, so I'll do something right now. What you see right now is considered to be the equilibrium. Okay, I will push it down here, and now I have displaced it which way? Downwards. There's a restoring tension acting which way? Upwards. So if I release it, so that oscillation is actually simple harmonic. Okay, so every time it goes down, it's trying to go up because of the force. Every time it goes up, it's getting compressed, right? The compression is pushing it which way? Downwards. Only it's because of weight, and it's actually like a wrong approach here. Weight does play a role, but according to the simple harmonic motion rule, এটা এভাবে করলেও কাজ করবে. And remember the animation I showed you, ওরা কিন্তু এভাবে করে, because এটা করলে advantage-টা কি? What's the advantage of doing it this way? Who doesn't play any role anymore? Yeah, weight. মানে এখানে যদি এভাবে করি, তাহলে আমরা ওয়েটটা সবসময় কোন দিকে অ্যাড করতেছে? ডাউনওয়ার্ডস। এখানে করলে একটা প্রবলেম, কেন? যখন নিচে যাচ্ছে, weight is acting helping you, but যখন উপরে যাচ্ছে, weight is actually opposing you. So isn't it like contradicting with some of the forces I have? So if you want to investigate a spring system, right, what are you supposed to do? Take it sideways and then attach it to a wall and put like a trolley there, like a car trolley, and the trolley will go back and forth like that. Okay, but এখানেও দেখতে পারবা, এখানে যেটা হয় আমরা ল্যাবে মানে আগে ছিল, এখন তো কোনো ল্যাব নাই। সো ল্যাবের মধ্যে যদি এটা করতা, you'd find that the simple harmonic equation doesn't work. It's not a straight line passing to the origin, and then students get confused, like, wow, what went wrong, right? What went wrong here? There's another force interfering with the process. What is it? Weight. But I mean, sideways করতাম, একদম perfect straight line আসতো. Okay, so the restoring force is this. When you pull it down, which way does it try to go? Up. When it goes up, which way does it try to move? Down, right? And it's always trying to come back to which location? The equilibrium. Okay, all right. So if it goes beyond the elastic limit, it doesn't follow a simple harmonic motion. We don't have that equation in our A levels, but there's a formula. T equals to 2 pi root m by k, and the k in that equation is a spring constant. So if your spring constant is distorted, right, it doesn't follow the rule anymore. Yeah, then friction becomes the problem, right? In a vacuum, horizontally or vertically? Horizontal in a vacuum. Vertically vacuum করলে same weight is an issue unless you're isolated space. হ্যাঁ, তাহলে perfectly কাজ করবে. Friction compensated. হ্যাঁ, বল. হ্যাঁ. Displacement is the opposite side. So আমরা consider করতেছি center to be the zero line. আর আমরা এই সাইডে ধরো পজিটিভ। সো আমি এটাকে পজিটিভলি ডিসপ্লেস করলাম। এখন ফোর্সটা কোন দিকে? ফোর্সটা কি এই সাইডে নাকি ভিতরের দিকে? হ্যাঁ, সো আমার ডিসপ্লেসমেন্ট পজিটিভ, ফোর্সটা কি নেগেটিভ। এটা যেখানে আসলো, এখানে আসলো, এখানে আসলো, ক্রস করলো, ক্রস করে এখন ডিসপ্লেসমেন্ট কি হলো? নেগেটিভ। ফোর্স কোন দিকে? Positive. So the idea is that displacement যেদিকে হবে, the force will always have to be in which direction? Opposite. That's what the negative sign means here. That's not bad actually. মানে but কি করাচ্ছে? Radioactivity. Something spinning like that. ওই যে একটা পাইপের ভিতর দিয়ে সুতা নিয়ে নিউটন মিটার। হ্যাঁ, it's fine. এটা কোনো জায়গায় আসবে না। Because তোমাদের প্ল্যানিং এ হচ্ছে experiments are not bound to the syllabus. I mean, it's not a bad thing. But the thing is, I think এই চ্যাপ্টার পরে কিছু করার নেই তো। রেডিওঅ্যাক্টিভিটি, কোয়ান্টাম মেকানিক্স, তারপর হচ্ছে নিউক্লিয়ার ফিউশন, এগুলো কি করবে তোমরা? Okay, question. See if you can tell me if they're simple harmonic or not. Okay, so number one, আমি obviously বলে দিচ্ছি বুঝানোর জন্য সবগুলো দিব. So you have a mass spring system. A mass spring system is very simple harmonic. Okay, it's one of the best examples out there. I'll explain them individually. Number two, the one we saw earlier. What is that? Pendulum system. So that's also very simple harmonic. But what about random scenarios? So I'll give you some that are a little confusing. So this one is a skate park track. So if you have seen like a skate park which is rollerblading like track থাকে, right? So ওই skate park-এর মধ্যে দেখবে এরকম একটা জায়গা থাকে where you can skate up and down like that, right? And there's a person skating here. Personটা হচ্ছে up and down যাচ্ছে. If you look at the person's says the skateboard, so the person will go from here like that. এখান থেকে start করবে উপর থেকে, and তারপর এখানে এসে তারপর will go back up like that, and it's a motion where it's energy conserved. So let's say there's no friction acting here. Okay, it's a perfectly smooth surface, no friction, no air resistance. The person will perpetually go where? Up and down, right? So my question for you is this person's motion simple harmonic or not? So I'll show you animation if you are not here. So animation হচ্ছে এটা. Right, so I'll make everything zero here. উপর থেকে start করলাম. So যে GP KE, GP KE, right? Forever. So bolo, is this simple harmonic or not? What do you think? Yes. How many of you agreed simple harmonic? Does it match all the criteria I've mentioned? So what were the criteria? Your acceleration and displacement must be in what direction? Opposite direction. And there must be a force acting towards the equilibrium or center, right? So do you think this person is undergoing simple harmonic motion? Yes. So does anyone disagree that it's not simple harmonic? Where's the central force? That's actually a good question. You know it's simple harmonic, but if you not then you will get a wrong answer. So, so the correct answer is no, it's not simple harmonic. And the reason behind that is it's kind of deceiving. And the reason why it deceives everyone is because it looks like, oh, there must be a force acting towards the center and whatnot, right? But when this ball here undergoes circular motion, try to figure out where the forces are. So it turns out there's one force coming from the wall of the skate part, that's reaction. That force will be broken down into two components. One component here, and there'll be one component acting which way? Up there, right? The thing that students fail to recognize here is where is the center? The center is actually this line here, right? So you can find there is a force acting towards the center, which is what? The blue part, right? And then as the thing comes here, আমার রিঅ্যাকশন ফোর্স কিন্তু চেঞ্জ হয়ে গেছে এখন রিঅ্যাকশন ফোর্স কোন দিকে অ্যাড করতেছে একটু উপরের দিকে সো এটা কি কমে গেল না রাইট আর এটা বেড়ে গেল আর ইউ উইথ মি রাইট বাট ডু ইউ সি সামথিং যে তোমার হচ্ছে এই ফোর্সটার ডাইরেকশন চেঞ্জ হয়ে যাচ্ছে রাইট অ্যান্ড অ্যাজ ইউ গেট টু দিস পয়েন্ট রাইট এই যে হিয়ার রেজাল্টেন্ট ফোর্সের কথাই তো আমি বলতেছি রেজাল্টেন্ট ফোর্সটা কোন দিকে অ্যাড করতেছে আপওয়ার্ডস রাইট did you see that how the force kept changing direction and is trying to aim towards what? That center there, right? But the object is not going around that center. The object is going around this line here. So the requirement is that the force should have always act which way? Straight to that line. Now you might be confused about this. I'll show ekhane tale tomader aro easy hobe. Why is a pendulum simple harmonic? So the reason behind that is you have your restoring force, right? Acting which way? Towards this line all the time. An object ki hobe ei jagate eshei thambe. So if I place it like this, and if I bring it from here to there, the other way, right? There's what acting on this rope? Tension. And the thing that's bringing it inwards is what? The component here, right? So if this is my angle here, theta, from the previous chapter, T equals to ki hobe? Or what is that force going to be? T sine theta. A sine theta ta kintu hocche equally vary kore with what? My motion here. এখানে notice করবা the moment it comes to the center, right? When it's actually at the center, this is 0, right? And the object is right at the center. And as it starts to go that way, a force tower develop হয়. and where does it start to point again? The other way. So it starts to point this way. This fulfills the simple harmonic requirement. Okay, not perfect. আচ্ছা এটা হচ্ছে আমি দেখি there should be an animation of this তাহলে একটু easier হবে বুঝতে right look at these. Okay, these are different examples of oscillations out there, right? So this one is not simple harmonic, because the force is not directly proportional to the acceleration. Okay, পরেরটা দেখি. This one is what I showed the cantilever is, right? This is actually simple harmonic, but এটা আমাদের syllabus নাই. This one is actually simple harmonic. So one of the most common examples of simple harmonic motion out there is a exact জিনিসটা না আমি বলছি কোনটা, ওটা হচ্ছে a piston in a car engine. So there are pistons out there, they pump, right? ওই piston গুলো যদি oscillation দেখো তোমরা, they actually follow a simple harmonic. আর একটা example হচ্ছে like a buoy, পানির মধ্যে float করে, ওটা যদি পানি নিচে press করো, right? It'll actually start to go up and down like that, right? It also follows simple harmonic. So there are random scenarios out there, but the idea is that if you want simple harmonic to work, there must be a force acting which way? Towards the center. This is like what the yo-yo does. Like, it spins in and then spins out. This is not simple harmonic. So you can take out just one of them was simple harmonic. This is simple harmonic. This is simple harmonic. Which is displacement directly proportional, because A equals to so TJ component equals to what? MA. So my acceleration to depend on that value, right? So যখন আমার center আসছে, so what is my displacement? 0, right? What is my acceleration as well? 0, right? ওই যে skate parkটা ওটার মধ্যে doesn't become 0. There's still some force acting on it because of gravity. So it should be 0 entirely. It shouldn't be any other force acting on it. Right, so এই দুটো একটু দেখে নেই before we wrap up. So এটা কি হচ্ছে আমরা এভাবে না দেখে what we'll do is we will look into this way, and what will I attach to my trolley here for movement? Wheels. And as one of you mentioned, it's true, what will become a new factor here? Friction. Okay, friction versus weight. Which one do you think has more detrimental effect on my simple harmonic motion? Why? So I'm বলি তোমার simple harmonic motion যদি করার চেষ্টা করি with the one I showed, right, versus this one, right, which friction actually involved, which one do you think will still show simple harmonic motion? Why? Isn't there an external force acting here? ওটা এখানেও ছিল, এইখানেও ছিল না. So I'm বলি এখানে friction একটা issue আছে, which is a good thing. Friction will always act to what of your motion? Opposite. So when you're trying to go left, friction is acting to the right. When you're trying to go right, friction is acting which way? Towards the left. It does follow and change direction. What was the problem with weight? When you're going up, weight is down. When you're going down, weight is also down. So therefore, it's not really like balancing out its issue, right? So friction থাকলে it doesn't really matter, but yeah, আমার যদি এটা হচ্ছে original setup থাকে, and I compress it মানে হচ্ছে I bring the trolley inwards like that, push it in like this. Can you tell me if I release it, আমার হচ্ছে যে এই লাইনটা is my equilibrium, right? Right now, which way did I displace it? Let's say negative, right? This spring that you see here is applying force which way? The opposite direction. So what is my direction going to be here? Positive. And a force will be there until the trolley reaches which location? Equilibrium. Equilibrium, can you tell me what the force should be? 0. And what is my displacement as well? 0. But then what it'll do is it'll cross this line. So it'll get cross for it, উল্টা দিকে আরো দূরে চলে যাবে। So go, let's say right, so এখান থেকে হচ্ছে it'll stretch the other way, springs, right? So it'll go same distance the other way, and as it goes the other way, the spring will now be extremely stretched. So it'll be something like that, right? Excess stretch হয়ে গেল, tension and everything. So which way is the displacement right now? Yeah, to the right. So my displacement is going to be positive because it went that way. And which way is my acceleration? The other way, because what is now pulling me back in? Tension, right? If I stretch this spring outwards, which way does it bring me? In. And if I compress it, which way does it push me? Out, right? So that's basically what's happening here. So I'm negative হয়ে যাচ্ছে. So yeah, that's why it's simple harmonic, because there's always a force acting towards the what of the motion, the center of the motion. Same goes here as well. এটাতে তা হচ্ছে না. So if you actually plotted a graph for this, এখানে আমি পাচ্ছি না animationটা, the graph is like this. The acceleration doesn't vary equally, okay? But if I plot a graph here for the acceleration that we have and the displacement that we have, what would you expect the graph to be? A straight line passing through the origin with a what gradient? Negative gradient. And more importantly, what does the gradient help you achieve? Yeah, so eventually quantity gradient থেকে বের করতে পারবো of my oscillation. Time period. That's a time period. No, angular velocity, yes, but time period. Because ওরা কি করে, they'll give you a random oscillation and they'll ask you graph থেকে find time period. So time period কেমনে বের করবো? We're going to find the gradient of this graph. The gradient of the graph gives you what? Omega square. Omega is what? 2 pi by t whole square. So the gradient allows you to find the time period. And you can do the reverse as well. Time period থাকলে you can find the gradient. The half circle যেটা এটা হ্যাঁ হ্যাঁ কারণ
সবটা ফ্যানের আমি কালকে স্কুল প্যাড দিছি
বাড়ি থেকে খাই তার লুজ হয়ে গেছে
কিছু একটা হইতে পারে।
কারণ স্পিড বাড়লে সাউন্ড বেড়ে যেত, মানে ফ্যানের সাথে বাড়ি খাচ্ছে। Thank you. Thanks. There's more if you want, by the way. শেষ হয়ে গেলে বলো। So I've written the reason here for it, bro. This blue arrow should be acting towards O at all times, but it's not acting towards O. O is the center of this oscillation. First one first.